The last time we were together, I mentioned that I wanted you to look up something about Madame Curie and the radium girls. I found this interesting video. Hopefully, my computer will play it, but who knows? It's a great video.
When May Keane died at the age of 107 in March 2014, reports of her death focused not on her extraordinarily long life, but on the fact that she probably should have died nearly 9 decades earlier of radiation poisoning. It's believed that Keane was the last of the so-called Radium Girls, a group of several thousand young female factory workers in the early 20th century who for years worked with one of the world's most radioactive substances and suffered the consequences. Nearly a century later, their story is a reminder that it can take us a while to fully grasp the downsides and side effects of new discoveries. And at the turn of the 20th century, radioactive elements were far from being fully understood. Radium was discovered in 1898 by Marie and Pierre Curie. They were interested in the fact that minerals containing the element uranium gave off electromagnetic radiation that could pass through metal. Marie Curie investigated these rays, focusing on the mineral pitchblende, where uranium is often found. She discovered the mineral gave off more radioactivity than can be accounted for by the uranium alone. Together, she and her husband succeeded in isolating both element 84, dubbed polonium, and element 88, radium, in the pitchblende. The spontaneous release of energy from rocks was as exciting as it was perplexing. It was considered to be a new force of nature, but little was known about radium's properties or dangers. It didn't take long for doctors to find that the application of radium salts to a cancerous tumor would often shrink the tumor. If it's good for shrinking tumors, it must be good for everything, right? So by the early 1900s, radium therapy gave birth to an entire industry of phony cure-all medicines and elixirs. Everything from radium soda to radium toothpaste soon appeared on shelves. Even radium water was a thing. Luckily for consumers, most of these products contained such low levels of radium that they were pretty much harmless. But then someone discovered how to turn radium into glow-in-the-dark paint. Radium itself doesn't actually glow, but Marie Curie famously described the blue fairy-like color she saw while working with the mineral. The effect is caused by the interaction of radium with other chemicals as it decays. As it decays, radium releases particles that ionize nearby materials, creating positively charged ions that pull negatively charged electrons from other nearby atoms. The glow occurs when electrons return to their original state, releasing that extra energy as light. In 1902, an inventor named William Hammer, who would be the first person to suggest using radium as a cancer treatment, used samples of radium salt given to him by the Curies and mixed it with glue and zinc sulfide to create a luminescent paint. Hammer found a variety of uses for this new luminous material, which he called undark, from toys to gun sights, but the most popular was for the dials on watches and clocks so they could be seen in the dark. By the early 1920s, undark was being used by the U.S. Radium Corporation in New Jersey, where more than 4,000 workers, mostly young women, used it to paint tiny glowing numbers on watch faces. Even though the company's own chemists made sure to handle radium behind lead shields, the radium painters weren't given much in the way of protection. In fact, workers were encouraged to use their lips and tongues to shape the tips of their brushes. Soon, the effects of the radium showed up in the health of the workers. Even though very high but very localized exposure to radium can kill cancer cells in some cases, ingesting large amounts of it over time exposes the whole body to its damaging effects. And what makes radium particularly dangerous when it's ingested is that it has chemical properties similar to calcium, so it's easily absorbed into bones, teeth, and other tissues. As a result, the women soon developed tumors, bone marrow damage, and leukemia. Others started losing teeth, suffering from deteriorating jawbones, mouth cancers, sores, and anemia. By the late 1920s, the health concerns about radium were starting to become public, and in 1927, 5 of the painters sued their employer for damages and medical expenses and won, but by then, dozens of past and present radium painters had died. That May Keane survived is probably due to the fact that she found the paint gritty and didn't like the feel of it in her mouth. To this day, if you run a Geiger counter over the graves of many of the women who died nearly 90 years ago, the needle will jump. Nearly a century after they introduced the world to the dangers of radium firsthand, the Radium Girls remain radioactive. Thanks for watching this SciShow Dose, brought to you in large part by today's President of Space, Soliloquy. You can check out his YouTube channel by following the link in the description. If you would like to become a president of space or just support SciShow and receive monthly rewards, go to patreon.com/SciShow.
Okay. Boy, was that guy high energy or what? Today we want to talk about what my calculator is trying to tell me. When we get answers of a variety of sizes, from very, very big numbers to very, very small numbers, your calculator has a problem because your calculator's window is only a certain length. And very, very big numbers or very, very small numbers do not fit. So that's what we're going to talk about today. So if you multiply two very, very large numbers, as I have done here, you would agree with me they are very, very big numbers. You get an answer something like that on the window of your calculator. The calculator, as I mentioned, does not have room for 19 or 20 digits on its window, so it puts it into scientific notation. We can talk about scientific notation. There are certain rules that you need to know. But essentially, it's used because the calculator runs out of room. All right, or you can also do it with a very, very small number. Like, for instance, this is a super tiny number. If you divide by a very big number, your answer is going to get even smaller. Much, 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 much smaller. Something like 21 digits after a decimal point, okay? Once again, the calculator puts it in scientific notation. Here's the rule for scientific notation. Scientific notation is expressing a number using a number between 1 and 10 and multiplying it times a power of 10. For instance, 400. Move your decimal from the end, move it over 2 places to 4, and you would have to take it times 100. But the rule is it's got to be a power of 10. 100 is 10 squared. A calculator would write it 4e2, where the power of 10 is the 2. So you can either write this answer 4 times 10 squared or 4e2. Small e or capital doesn't matter. 7 thousandths. Right here, 7 thousandths is a tiny number. That's 7 times 1,000th. 1,000th is 1 over 10 cubed. The 10 cubes on the bottom. If you flip it, we talked about that one other day in here. If you flip it, it becomes 10 to the minus 3. So scientific notation is 7 times 10 to the minus 3, or 7e to the minus 3. Okay. Let's do a few more. 0.000357. Move the decimal point 4 places, so it becomes 3.57. Now, you moved it 4 places, and it was a tiny number. If you mess this up at all, it'll be because when you move it 4 places, you don't know whether to write it 10 to the 4th or 10 to the minus 4th. Here is the way you should remember that. Tiny numbers, negative exponents. Big numbers, positive exponents. That's the easiest way to remember this, okay? 0.000357, the decimal is here. You have to get a number between 1 and 10. So you move it back 4 places. So it becomes 3.57 times 10 to the minus 4 because it was a tiny number, or 3.57 e to the minus 4. Big number? That's a big number. The decimal is over here. You have to move it this way 8 places. You get 2.35 times 10 to the 8, positive 8, because it's a big number. That is the absolute easiest way to remember that. Or 2.35 e to the 8. Changing some around here. Let's just do a few of these. Decimals at the end, move it 3 places. This one becomes 4.40. You can round off to hundredths, times, we moved it 3 places, and it was a big number. So it's a positive 3. Tiny number, move it 2 places, 3.08. Because it's a tiny number, it's a minus 2, right? That's all there is to this. Very, very easy. Now let's go the other direction. 5.29 e to the minus 3. That's in scientific notation, the way your calculator would do it. How do you change it? Because it's a minus 3, it must have been a tiny number. So to get a tiny number, you have to go to the left 3 places, and there it is, 0.00529. Next one is, once again, a very tiny number, okay? Very tiny number because it's a negative power. You must move your decimal point 6 places. So I'm going to move it. I'm going to have to add 5 zeros. And if you want to, you can round off. So then it would be 106. Yeah? I've moved it over 1, 2, 3, 4, 5, 6 places to make a tiny number. Why tiny? It's a minus. 3 times 10 to the 7th. The 7 is a positive number. You know it's going to become a big number. The decimal is right here. To be a big number, you have to add 7 zeros. 2e5, positive 5. The decimal is after the 2. You're going to have to add 5 zeros. Let's do one more tiny one. Negative 2, you know it's going to be a tiny number. If you go 2 this way, you're going to get 309. That's a big number. You have to go 2 this way, and you get 0.030924. Tiny number because of the negative power. Okay, now, make sure I'm on the right page. Second part of our day today, we're going to work a little bit on probability. I have the feeling you'll find most of these to be incredibly easy. Try to keep your answers in decimal so we're all doing them the same. Definition of probability is what you want on the top of the fraction divided by, on the bottom, the total number of possible outcomes. For instance, tossing a coin, I want the probability of a head. What I want is one outcome, a head. On the top and on the bottom, you put a 2 because there are 2 possible outcomes, a head or a tail. How about down here? I have 3 red, 5 blue, and 6 white. What's the probability of getting a blue? What I want is blue. There are 5 ways to do that on the top. On the bottom, there's a total of 14 possible outcomes. And your answer then, changed to a decimal, would be 5 divided by 14, or 0.36, or 36%. The probability of a red or white is 3 plus 6 is 9, divided by 14, change it to a decimal. The probability of getting a red and a white at the same time is 0 because they are different colors. You can't get 2 colors at the same time. Standard deck of cards. There are 52 cards in a deck, standard deck. There are 4 suits, hearts, diamonds, spades, and clubs. Hearts and diamonds are red, spades and clubs are black. Numbers in each suit, 2 to 10. Jack, queen, king are face cards, and ace is not a face card, and it's not a number. So the probability of getting an ace, there's 1 in every suit. There are 4 of them out of 52. You can reduce it. I would just change it to a decimal, 4 divided by 52. The probability of getting a black king, there's a king of clubs, a king of spades. That's 2 out of 52. Change it to a decimal, 2 divided by 52. The probability of getting a red card, there's 2 ways you can do it. Hearts and diamonds are red, 13 cards each, makes 26 out of 52. Or why not just think half the deck is red and half is black? So the probability of getting a red is 1 out of 2. The probability of getting a queen or a heart. Now you got to be careful here. Getting a queen, there are 4 queens. Getting a heart, there are 13 hearts, 13 in each suit. But the problem is, you counted the queen of hearts twice. So 4 plus 13 is 17. You got to take one off because you counted the queen of hearts twice. 16 out of 52. Divide it. 16 divided by 52 to get a decimal. And I get about 31% of the time. You'll get a queen or a heart. What about getting a queen and a heart? A queen and a heart at the same time you can do if you get the queen of hearts. That's 1 out of 52. Okay? Now, another way you can do this problem, you could say the probability of getting a queen is 4 out of 52. The probability of getting a heart is 13 out of 52, and you can multiply it. When you want to do an and problem, and the events are independent, having nothing to do with each other, you can multiply them. Toss a coin and a die. What's the probability of getting a head and a 2? Now we'll come back to what I just said about multiplying. The probability of getting a head is 1 out of 2. The probability of getting a 2 on one die is 1 out of 6. Your chance is 1 out of 12. Okay? Or the other way to do it, toss a coin and a die. What are you going to get? You're going to get a head and a 1, a head and a 2, a head and a 3, a head and a 4, a head and a 5, a head and a 6, a tail and a 1, and so on. And you can see to get a head or a 2, another way to do it is 1 out of the total of 12. Isn't probability fun? Okay, 20% of the class likes ice cream, 30% of the class likes French fries, 10% of the class likes fries and ice cream. What is the probability of getting someone who likes fries or likes ice cream? Or you can say the probability of getting someone liking fries is 30%. The probability of getting someone who likes ice cream is 20%. So you can add those two. But whoa, hold up. You counted some people twice. You counted the ones that like fries and ice cream at the same time. Fries and ice cream is 10%. You have to subtract that off because you counted them in each group. Answer, 0.40. Okay? Liking fries and ice cream is 10%. There are 40 students in a class. 80% like classic rock. And of those who do, 20% like the Rolling Stones. What's the probability that someone likes the Rolling Stones? So let's start. There are 40 students in a class. 80% of them like classic rock. 80% of 40, there are 32 that like classic rock. Now, out of those 32, 20% like the Rolling Stones. Take that times 0.20, and I think you get 6.4. There are 6.4 students who like the Rolling Stones out of the 40. So 6.4 divided by 40. What's the probability? Is 16% chance of getting someone who likes the Rolling Stones. Okay? Okay. 8 coins, 8 white and 6 black. You select a white coin and you set it aside. Find the probability of a black on your next draw. You set a white coin aside. There are now only 7 whites and 6 blacks. So what's the probability of getting a black? What you want? 6 black out of a total of now 6 and 7, 13. So it should be 6 out of 13. Are you with me? What's the probability of getting 2 blacks, one right after the other, and if you don't put the first one back? the probability of getting a black the first time is 6 out of 14. And you want to get a black on the second one, but now we set it aside. So now there's only 5 out of 13. Okay? And you can multiply and divide. The probability of getting 2 blacks on successive draws is 30 on the top, divided by 14 times 13, and I get a chance of 16% of getting 2 blacks. Okay? Toss 3 coins. List all the outcomes. Okay. I could have head, head, head. I could have head, head, tail, head, tail, head, tail, head, 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 tail, 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 head, tail, or head, tail, tail, or 3 tails. 8 possibilities. Find a probability of 2 heads and a tail, 2 heads and a tail, 3 out of 8. 3 heads, 1 out of 8. No heads, 1 out of 8. Okay? I'm going kind of fast because I'm assuming you guys are all thinking this is really easy. Suppose there's 500 males and 600 females at SU. To be a drawing of 1 male and 1 female. I predict I can tell you who will be drawn. Find a probability that I can do that. The probability of me getting the guy right is 1 out of 500. Yes? Times, because I also have to get the female right, 1 out of 650, okay? Which is going to be 1 divided by 500 times 650 is scientific notation. Scientific notation because the calculator didn't have room. It should be. That's my chances of doing it, okay? Not very likely. Okay, your assignments on Blackboard once again. We've only got a couple days of regular classes left. Good luck with the problems. I think you would find this assignment to be pretty easy. See you next time.